Hello, everyone. Today, we are diving into one of the most critical aspects of food manufacturing: how we choose and optimize our processing techniques. Whether you're in quality assurance, operations, product development, or management, these decisions directly impact your bottom line, from product safety and shelf life, right through to your sustainability footprint and market positioning. We will walk through the main processing families, look at their trade-offs, and discuss how industry leaders are balancing these three pillars: quality, safety, and sustainability. So, we will walk through the main processing families, look at their trade-offs, and discuss how industry leaders are balancing these three pillars: quality, safety, and sustainability. This module delivers an in-depth understanding of key food processing methods, exploring their influence on product quality, safety, and sustainability. Learners will acquire knowledge of classical and emerging processing technologies, examine their impact on nutritional and sensory food attributes, evaluate safety considerations including microbial and chemical hazards, and discuss sustainability implications such as energy use and waste reduction. This content prepares learners to critically assess processing choices within modern food systems. After completion, learners will be able to explain the different food processing techniques in terms of product quality, safety, and sustainability. Let's be honest, consumers buy a finished product, not a processing technique. They want a yogurt that tastes great, is safe, lasts 2 weeks in the fridge, and comes in recyclable packaging. But behind that simple product is a complex web of decisions. Processing is how we achieve all three things simultaneously. Primarily used for milk and fruit juices, pasteurization gently heats liquids, killing most bacteria while preserving flavor and some nutrients. This process reduces foodborne illnesses without adversely affecting sensory profiles. Alternative pasteurization methods like ultra-pasteurization, UHT, use higher temperatures for shorter times, allowing longer shelf life but at more nutrient loss. Application of high temperatures, greater than 100 degrees Celsius, to destroy all microbes and spores, enabling shelf-stable products. Sterilization applies higher temperatures to achieve commercial sterility, enabling long shelf lives at ambient temperatures. Canning involves filling sterilized food into sealed cans or jars and subsequent heat treatment. These methods destroy spores, eliminating spoilage issues and making canned goods reliable food sources. Brief heat treatment, usually boiling or steaming, applied to vegetables or fruits before freezing or drying. Used primarily on fruits and vegetables prior to freezing or drying, blanching inactivates enzymes that degrade food quality, preserve color, and reduce microbial load. It involves quick boiling or steaming for seconds to minutes, minimizing nutritional losses and ensuring color and texture retention. Ultra-high temperature, UHT processing is a thermal food processing technique where liquid foods, typically milk and juices, are heated to very high temperatures, around 135 to 150 degrees Celsius, for a very short time, about 2 to 5 seconds. This process sterilizes the product by killing all microorganisms, including spores, and inactivates enzymes that cause spoilage, enables products to have long shelf life, typically 6 to 9 months, without refrigeration, making it ideal for storage and transport. Nutrient degradation. Heat-sensitive nutrients, particularly vitamin C, thiamine, and folate, degrade during thermal processing. The extent depends on temperature and duration, prompting optimization efforts in industry to balance safety with nutritive value. Microbial reduction. Thermal processes ensure inactivation of foodborne pathogens such as Listeria, monocytogenes, and Clostridium botulinum, critical for consumer safety. Energy use and innovations. Thermal processing consumes significant energy. Innovations include microwave-assisted sterilization, ohmic heating, electrical resistance heating, and continuous flow systems enhancing energy efficiency while preserving food quality. These techniques apply controlled heat to kill or deactivate microorganisms and enzymes responsible for spoilage and potential health hazards. Product quality. Heat treatment improves digestibility and deactivates enzymes that cause food deterioration, but can reduce heat-sensitive nutrients like vitamin C and certain B vitamins. Overheating may cause undesirable texture or flavor changes such as toughness or browning. Techniques like blanching and ultra-high temperature (UHT) processing optimize nutrient retention while ensuring safety. Safety thermal methods are foundational in eliminating pathogens such as Salmonella, Listeria, and E. coli, significantly reducing foodborne illness risks. Sustainability. These processes require substantial energy input, contributing to greenhouse gas emissions. Recent advancements focus on energy-efficient equipment and alternative heat sources to reduce environmental footprints. High hydrostatic pressure processing (HPP) uses intense pressure to deactivate microbes without heat, preserving nutrients and fresh taste in juices and meats. Pulsed electric fields (PEF) applies short high-voltage pulses to kill microorganisms in liquids, maintaining nutritional quality with low energy input, aligning with sustainable and clean label trends. Ultrasound disrupts microbes via cavitation, improving extraction and preserving heat-sensitive nutrients. Ultraviolet light disinfects surfaces and clear liquids without residues. Cold plasma uses reactive gases to inactivate pathogens on food and packaging at low temperatures, preserving texture and flavor with minimal environmental impact. Ohmic heating relies on electrical conductivity of foods. When an alternating current passes through food placed between electrodes, the electrical resistance of the food converts electrical energy into thermal energy, heat, uniformly throughout the product. Microwave heating uses electromagnetic waves to directly heat food materials. The energy causes polar molecules, predominantly water, to oscillate rapidly, billions of times per second, attempting to align with the alternating electric field. Radiofrequency heating uses electromagnetic waves at a lower frequency range, like microwaves. RF induces heating via dipole rotation and ionic conduction, but provides greater penetration depth, allowing more uniform heating in thicker or denser food products. The oscillating electric field causes polar molecules and ions to move, generating heat inside the food. Non-thermal processing methods consume significantly less energy compared to traditional thermal techniques, making them more sustainable. These technologies preserve heat-sensitive nutrients and maintain fresh-like qualities such as taste and color by avoiding prolonged heating. Energy-efficient innovations like microwave-assisted sterilization and ohmic heating offer uniform and rapid processing while reducing nutrient degradation and environmental impact. Mechanical processing alters foods' physical properties, enhancing texture, appearance, and nutrient bioavailability. Techniques include cutting, grinding, peeling, emulsification, homogenization, and extrusion. These methods improve uniformity and facilitate further processing. Proper hygiene and equipment design ensure safety by preventing contamination and removing undesirable components. Chemical additives enhance shelf life by inhibiting microbial growth and oxidation. Preservatives prevent spoilage, while antioxidants delay rancidity. Natural additives such as plant extracts and microbial metabolites align with clean label trends and consumer demand for fewer synthetic chemicals. All additives must undergo strict safety evaluations and clear labeling to ensure regulatory compliance and consumer safety. Fermentation uses microbes to produce acids and antimicrobial compounds, enhancing flavor, safety, and nutrient bioavailability. This process lowers pH, inhibiting pathogens, and supports probiotic health benefits. Waste valorization through fermentation converts byproducts into valuable ingredients, promoting circular economy practices and sustainability by reducing environmental impact. That's the landscape. Processing techniques are not isolated choices. They're intertwined with your market position, your cost structure, and your sustainability trajectory. The winners in the next 5 to 10 years will be companies that figure out how to optimize all three pillars simultaneously. Companies that can say, our product is safer and fresher and more sustainable than the alternative, and back it up with data. If you're curious about your own facility's potential, I'd encourage you to do a process audit. Map your current thermal load, identify where energy is consumed, ask whether emerging technologies could fit. Sometimes a modest investment in more efficient equipment or a hybrid approach unlocks significant competitive advantage. Thank you.